In this video, we're going to go over section 2.4, application problems involving exponential growth. 2.5 is very similar. 2.5 will be much shorter. I think I will go ahead and go over the first 2 pages first, and then come back and do the 3rd page and the 4th page with 2.5, because the page 3 and page 4 are somewhat similar to the type of problems that we will see in section 2.5. So let me go ahead and go over the first 4 examples of section 2.4. The blank note is posted on Canvas. When I am done with this, I will also post the completed notes. Okay, alrighty. So example 1, in 2019, an art collector pays $75,325,000 for a particular painting. Wow, okay. What kind of painting? Out of curiosity, I was trying to Google. All right, anyways, the same painting sold for $55,000 in 1960. So it went up a lot, as you can see. It was only $55,000, and I say only compared to this $75,325,000. So over, however many years, the painting became very expensive. So let's see what we are doing here. Complete parts A through D below. Find the exponential growth rate K. We used R when we were doing exponential functions to 3 decimal places, and determine the exponential growth function V, for which V of t is the painting's value in dollars t years after 1960. Round to 3 decimal places as needed. Okay, we can do this. Now, assuming this painting's value is continuously compounding, not like compounding at the end of every year, or end of every month or every day, it's reasonable for us to assume continuous compounding. I will go ahead and write that formula. A equals P times E raised to the R times T power. Now we do know what P is. P is how much this painting was in our base year of 1960. So this painting was 55,000. So that is going to be our principal. And R, the rate, is unknown. That's what we are trying to find. Now, they did use the variable K. So I'll go ahead and instead of using R, let me go ahead and change this to K then. Okay? Instead of RT, we're finding KT, where K is the exponential growth rate. What do we know about T? How many years is 2019 from 1960? So to find that, let me go ahead and subtract 2019 minus 1960. Okay, so that's like what, 70, not 70, I'm sorry, like 49 years. 2019, I can't subtract in my head. Okay, 59 years. 59 years. So T is 59. So let's go ahead and plug in these. Oh, you know what, guys? We know one more value. We know that the ending amount, the ending value in 2019 is $75,325,000. So we have these 3 numbers, P, T, and A. Let's plug them into P, T, and A. You ready? So that will be 75,325,000 equals 55,000 times e to the k times t of 59. Okay, let's solve this. I'm going to go ahead and divide both sides by 55,000. I don't want to round this problem, round this in the middle of a problem, so I will just go ahead and take away these 3 zeros and just write the fraction as 75,325 divided by 55. I guess you can get a decimal, but I didn't want to round it in the middle of a problem. And the right side will be e raised to the 59 times k. Let's solve this by taking natural log of both sides. If I take natural log of both sides, I will get natural log of that fraction, 75,325 over 55. And if I take natural log of this side, guys, natural log of E will cancel out, right? Well, that will just give us 1. So I will get 59K. You see, the last step to solve for K is to divide both sides by K. So K is natural log of, I hate writing this fraction over and over again. It's just so big. And we're going to just go ahead and divide that by 59. Let's do that on our scientific calculator. By the way, I did have a mistake on my first lesson video for the day. Y-intercept on example number 4 was incorrect. I typed in the wrong thing when I was using my cell phone calculator, but I did fix it on the note. Now I had to grab my, actual calculator because I don't want to make any more mistakes. So K, we found it. So what's that in percent? It's going to be 12 point, how did they want us to round it? 3 decimal places? Well, I'll just say 12.2%, and I'll just round that decimal to 0.122. Okay, so we found it. Now let us write the equation that V of t. V of t is equal to the initial value of 55,000 times e raised to the K of 0.122, but T, let's leave it as T because we're not always looking for the painting's value in 2019. Because this 59 was corresponding number for 2019, but we should be able to use this function to figure out the value of this painting in any given year. So that's it, we found the equation. Now we're probably going to use this on part B, C, and D. All right, let's take a look. Predict the value of the painting in 2030. Now for 2030, guys, T is 2030 minus 1960 because 1960 is our base year. So 2030 minus 1960 is at 70. That is 70. So we're going to go ahead and find V of 70. Plug in 70 into the function that we just found. 55,000 times e raised to the 0.122 times 70. It should be more expensive than $75 million, right? Because 2030 is in the future. Okay, let's go ahead and type this in. 55,000 times e raised to the 0.122 times 70. I wish I can show you guys my calculator, but I'm really just typing this in. This is so big. I'm going to go ahead and write the number down first, and then I will put some commas. 2813,439.90 cents. All right, let me put some commas because this number is big. For every thousand, let me go ahead and put the commas. So I got the answer. Now take a look at this very special rounding rule over here. Round to nearest million as needed. Like, this is so expensive, we're not going to care about anything smaller than $1 million. So let us round this carefully. This is equal to 281. Now notice the rest of it. We can buy a small single house in Stafford with that money. Can we? Yeah, we can. But that's too small for this art paint, the value of this painting. So I'm just going to go ahead and just throw that out and say $281 million. Yep, that is our final answer. Now, if this number was bigger than 5 or equal to 5, then I would round up and say $282 million. But because that number was 3, I rounded down. We threw away $343,939.90 because it was smaller than 500,000. Okay, let's keep going. What do they want? Estimate the rate of now finally we're doing calculus. Rate of change of the painting's value in 2030. We can find the T. Well, we do know T is equal to 70. We did use that year in part B, so we do know that T is 70 for 2030. But when they say rate of change, we're talking about the slope of a tangent line, right? How fast is this painting's value changing? We know it is positive because this painting's value is going up like crazy. So let us find this by first finding V prime of T. Okay, so you know what? Let me go ahead and write down what V of T is first. The function is 55,000 e to the 0.122 times t. So if I want to find the derivative of that, the 55,000 stays the same. I'm going to multiply this by that e to the 0.122t. But when I take the derivative of this power, we're going to get 0.122. We have to multiply it by that. Okay? So let me go ahead and combine or multiply these constants. Multiply 55,000. And you know, guys, what rule did we just use? We use chain rule. This number is there because we found the derivative of 0.122t. We used the chain rule over here, but we talked about this like crazy on Monday, so I'm going to go ahead and just somewhat use this shortcut. So 55,000 times 0.122. The derivative function will have a coefficient of 6710 e to the 0.122t. Let's go ahead and use this and plug in t equals 70. The derivative at 70 is equal to 6710 times e to the 0.122 times 70. Carefully typing this into my calculator. I'm expecting to see a big number. That times e to the 0.122 times 70. Okay, I got a big number. I'm going to go ahead and write it down and then put the 1,000 comma. Okay, I'm ready. So here we have it. So I got 34 million. Now this is too big to be true, I feel like. But okay, maybe that is true because this painting is just so expensive. All right. So again, because it's so big, they wanted you to round to nearest million as needed. So let's go ahead and write down. This is rounded. I'm getting these emails. What's going on? I'll check that later. Rounded to 34 million dollars per year. Oh my goodness. What an investment, guys. What did I do? I threw away this amount of money. All that. Because that was smaller than 500,000. I didn't round up. I just round down to $34 million per year. This is an amazing investment if I can find something like that. So this painting is going up by $34 million per year in 2030. And this rate will change. You see how exponential growth, this rate is actually going to go up. So if you're talking about like in the future, 2050, if you follow this pattern, it's going to be much more than that. Wow, this is crazy. All right, let's do part D. How long after 1960? How long after 1960? They're asking, what's the T value here? Okay, how long after 1960 will the value of the painting be 1 million? Oh, okay, it's a good question. Because it wasn't quite 1 billion. It wasn't quite 1 billion in 2030. In 2030, it was $281 million. So how many more years will it take? So let's go ahead and say 1 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stick those 9 zeros. Okay, and we're going to say that's equal to our V of t. Okay, so I'll write down what I'm doing over here. Set V of t, the value function, equal to 1 billion. That's what we are doing. Do not set it equal to the rate of change function, not the derivative function, but the value function, because V of t is what we use to find how much the painting is. So that's equal to 55,000 times e to the 0.122 times t. And t, leave it as t because we're trying to figure what that is. Now divide both sides by 55,000. Let me try to see if my scientific calculator will simplify this fraction. Let me just get rid of these 3 zeros first. 1 million divided by 55. It's giving me a decimal, so I may just divide it by 5. 1 million divided by 5, and then I can write down 200,000 divided by 11. I just reduced the fraction. We don't really have to reduce the fraction. This almost as long as the other one. All right, but this is canceled out. I have e to the 0.122t. Okay, now let us go ahead and take natural log of both sides. Before I do that, let me minimize this a little bit. I should add more room in between problems here. Natural log of 200,000. If you're wondering, where did you get this fraction from? I just reduced that big fraction. Over 11 equals, now I'm going to write it, but I will erase it. Natural log of e raised to the 0.122t. What will happen over here, guys? This will come in front of this natural log expression. And natural log of e, that's just 1. So the only thing that we will have left is not in yellow, sorry, 0.122t. Okay, so let's solve for t. T is equal to, we're going to divide this natural log of 200,000 over 11 by 0.122. So make sure you close that parenthesis after natural log though. So I'm going to go ahead and type this into my scientific calculator. I do miss you guys. I want to ask you questions like, hello, do you have an answer? And somebody will give it to me. All right, I got 80.39. Okay, I just rounded to the nearest 100th. Okay, now, so it's going to take about 80.39. So it's going to take 80 point, I'll just round it up to 4 years. So I can say I'm going to go to 1960 plus 80.4 is 1960 plus 80.4 is, oh wow, in 2040, it's 2040.1, so I will say 2041. In the year 2041, oh wow, this painting will become $1 billion. But they just asked for how long after 1960, so I really don't need to figure out what year. So I'll just stop after getting 80.4 years later. So we can convert that into month too, but that's probably enough. Alrighty, let's go ahead and look at number 2. So this function, this section, entire examples that I got for you, they're all exponential growth. So the numbers are going up. Section 2.5 is almost the same thing, but they're going down. All right, let us see. In 1755, Sue's fifth great-grandfather's parents bought some cows for $35. Okay? Suppose that they had instead put that $35 in the bank at 4% interest compounded continuously for me. How much money will I have today then? Their $35 invested at 4%, compounded continuously. How much money is that going to be in 2020? Let's see. So for compounded continuously, you do want to write down that formula. And then let's write down everything we know. A is the amount of money that I would have had in 2020. P is $35. The cows were 35 bucks. E raised to the R is 0.04. And T is what? Well, we got to figure out what T is. Let me write down what everything is, though. I was excited to figure out if I'm going to be a millionaire then. But P is 35. Okay. R is 4%. So I'm using 0.04. And T is how many years after 1755? So I'll do 2020 minus 1755. So how many years ago is that? 2020 minus 1755 is 265 years ago. Okay, so 265, what was South Korea like? Probably still like Chosun era, probably not even banks or any kind of investment. But anyways, all right, I'm going to go ahead and plug this in. So $35 per cow, that would have been a crazy amount of money. 35 times e raised to the 0.04 times 265. Guys, I'm reading it. I am typing this into my calculator. Okay, I got an answer. Oh dear. I got 140.4719.31. Let's put some commas to figure out how much this is. $719. Oh dear, I would have had a million, a close like $1.5 million if they invested for me. Wow, okay, so did they ask me to round this somehow? No, it really didn't ask me to round this anyhow. So that is it. The answer is $1,404,719.31. That's the power of compounding. Okay. Not as extreme as 265 years, but I am investing for my retirement for about 30 or 35 years. So hopefully my money will grow more than that because I'm putting more than $35. But it's different because I'm putting more money every month instead of just one amount of money. Anyways, let's keep going. I love these examples because, I mean, first of all, we're talking about a lot of money. But what else can we talk about? Guys, this one is from my spring semester, my fall semester or spring. I can't remember. When Corona first happened, I was like, it was before spring break. Do you guys remember? Like in March, we had a spring break and school told us to don't come back because of coronavirus. And I was supposed to go to this the training in New York City. And I was like, should I go? Because Corona wasn't that serious back then. Now I am so thankful that I didn't go. But anyways, this example I created before it first happened in China. And then where I originally came from, South Korea, was hit pretty bad too because they were right next to each other. So this was the example back then in 2019. Or actually, you know what? That's still 2020. This year is 2020. Anyways, let's get back. In South Korea, the number of cases reported in the COVID-19 outbreak increased from only see, it was so small back then. 1,223 on February 26th to 3,400 in March 1st. Now, back then, this was a big number. I was like, oh my goodness, that country is... But now these numbers are like so small compared to what's going on right now, right? Anyways, so let's go ahead and find the exponential function that fits the data. Assuming continuous compounding. I need to calm down. Why? Because a virus ain't going to wait for end of the day or end of the month to compound. They're going to just spread continuously. So it's reasonable to assume continuous compounding. Let's see. A is the ending amount in March, 3,400. And P is how many people were sick in the first year reported. The first time it was reported in February 26th. So I'm going to use that. Now R, we don't know the rate. That's unknown. But T, guys, let's do this for days. Because, listen, Corona is not going to... Yeah, we should know. Because I check on my Facebook. Not as much anymore with the election and everything. Because that's more fun to watch. How many days is it? So, February 26th to March 1st. I forgot. Let me go back to my calendar. That's a long time ago. So I should update my example from... So I'm counting. 1, 2, 3, 4, 5, 6. I forgot the date. Was it March 1st? Was it March 1st? Yeah, it was March 1st. So let me count again. 1, 2, 3, 4. So 4 days. 4 days. In 4 freaking days. It grew that much. All right. T is 4. And I'm going to use... T is in days. I'm not going to use years for coronavirus spread, right? All right, so let's go ahead and plug these in. A is 3,400. P is 1,223 times e raised to the rate we don't know. We want to know how fast this is spreading. And T is in 4 days. All right, let's go ahead and first divide both sides by 1223. I wish you guys are watching. I really hope you guys are watching this. Drop me a comment or something like that. All right, I tried to get a decimal and it wasn't that nice. So I'm going to go ahead and just try to write down the simplified fraction. And this is not going to be simplified. They're relatively prime. Oh, wow, I am low on my iPad. Let me see if I can try to finish this before my iPad dies. I am having one of those days, guys. And I really appreciate your understanding. All right, r times 4, that's just 4r. Let's take natural log of both sides. If you take natural log of both sides, we're going to have natural log of that fraction divided by this. And that right side, is it okay if I just go ahead and write down 4r now? I think you're okay now. All right, so the rate is going to be this natural log of 3400 divided by 1223 divided by 4. Because we have to divide both sides by 4. All right, let me type this in my calculator. So my third video will come after me charging my iPad a little bit. So 0.2556. That's 25.56% growth rate. That is crazy. I should look up Ebola and SARS and different ones. I'm just, curious. But listen, guys, these numbers are from an actual report. I think I looked up CDC somewhere, or not somewhere. I looked it up, maybe Korean CDC, but I can't say this is the actual growth rate of the virus because more data became available, so things are changing. But back then, looking at this very short period of time, that's what it is. All right, let's write the function. So the function is, let me write C of t. C stands for coronavirus. Our C of t is equal to 1223 times e raised to the 0.2556. Now what we just did is we came up with an equation, okay? But now, can we apply this to the entire world? Can we apply this to China or United States or the entire world? Not really. This data is only from South Korea, only in a 4-day period. So we should not extrapolate. We should not use this model to predict anything else, okay? Just within like a close window of in Korea. All right, let's see. Use the model to predict how many people will become infected by March 3rd. Okay, March 3rd. March 3rd is, all right, look at me what I'm doing. I'm going back to my calendar. 1, 2, 3, 4, 5, 6. That was a superset Tuesday, huh? But that's 6 days after our first report. So it's 6th day from February 26th. February 26th is the base day that I'm using. So let's see. So I'm gonna go ahead and find C of 6. So 6 days later, how many people are infected in South Korea? And it was, I think, the very next class, or like the next week, in this particular class, we actually checked the number and we were pretty close. Okay, let's go ahead and type this in. All right, what did you guys get? I got 5,668.399. So I will just go ahead and round it to the whole number of people. And back then, my students and I were like, oh my goodness, that number is big. But compared to what's happening in November of 2020, this number is just a cute number, huh? All right, let's keep going. How long will it take for the number to reach? Okay, guys, it's only 10,000. Now I'm saying like only 10,000, but now we should probably look at like 1 million, right? But okay, I'm gonna go ahead and do this problem. 10,000. So 10,000 equals the function 1223 times e raised to the 0.2556 times t. We're gonna figure out what t is, okay? Divide by 1223. I just realized this isn't really calculus. This is definitely pre-calculus, but this is fun. All right, so I'm going to have that fraction, 10,000 over 1223 equals e raised to the 0.2556 t. Take natural log of both sides. You guys solve this type of equation so many times already with me. You do know how this is going to go. And if I take natural log of this side, you remember what happened. We're just going to have that 0.2556t coming down. All right, so t must be, if I divide both sides by that decimal, natural log of 10,000 over 1223 divided by 0.2556. So how many days will it take for South Korea to, I mean, it already happened, but let's see. Back then, since I was on a maternity leave, guys, in the fall semester, like in the summer and a little bit of fall, and you know, I did not get to update my examples from last semester. So that's why you're looking at some old data. So I got 2.8.22 days. So it's gonna take them 2.8.22 days from February 26th. So let me go into my calendar and see. 1, 2, 3, because coronavirus doesn't take Saturdays and Sundays off. 1, 2, 3, 4, 5, 6, 7, 8. Around March 5th. That sounds so short. But that is what it is. That is what it is, really. Wow. This is very fast. Alrighty. Something must be happening. I'm gonna check that email later. I think I'm getting some very sad news in my email, because I never get that many emails from other than from students. All right, let me do the very last example, example 4, and I will stop, because I think page 3, this is gonna be similar to actually 2.5, how I set up my examples in 2.5, I think. So let me do the last one, and then I will stop this recording, okay? The number of women graduating from four-year college in a particular country grew from 1930, when 53,215 women earned a bachelor's degree, to 2005, oh wow, approximately 671,000 women received such a degree. Ah, yay! Okay, so let us find the exponential function that fits the data, assuming continuous. Because, I mean, okay, a lot of people graduate in May or January, but people can graduate in, you know, some schools offer graduation another time, like if a school is going by quarters. So I'm just going to go ahead and use continuous, okay? Okay, and then I can say that A is the ending amount, 671,000. I can say P is how many graduated back in 1930, 53,215. R is unknown, we don't know the rate, but T we can find out the time. How many years did it took for that change to happen? 2005 minus 1930. Okay, 2005 minus 1930. And that comes out to be 75 years. All right, in 75 years. All right, what's the rate then? We're going to plug in the numbers in here. 671,000 equals 53,215 times e raised to the r times t. So I'll go ahead and write down 75t. I'm sorry, 75r, okay? Because r is the unknown. All right, let's divide this both sides by that number. So I think, do you guys see the similarity? Like, they're very similar, right? And then, you know, the next step, I'm going to take natural log of both sides. So I feel like you guys are seeing how these equations are all very similar. I'm kind of skipping some steps. Natural log of e to the 75r is going to just turn into 75r, which means r is equal to natural log of. I'm sorry if I was going a little too fast on the previous step, but I'm sure if you were paying attention to all these emails, my previous examples, they are very, very similar. All right, let us get that decimal, that rate. I'm gonna go ahead and type this in. And don't just trust me, because who knows, I am a human being too. I may type in a wrong number in my calculator, so I want you to confirm it for me. I got 0.0. Did they mention anything about rounding? They didn't. So 0.34. I'll just round it to the 10,000th place. So about 3.4% growth rate. To me, that is not fast enough, but that's still a growth. All right, here's the equation then. A equals 53,215 times e raised to the 0.034 t. This is the function that will help us. And you know what? Instead of just calling it a, let's call it a of t. Or I could have called it w of t for a woman. All right, but that is the function. That's the exponential function that fits the data. Find the exponential growth rate. Okay, exponential growth rate. Hey, we found it. Exponential growth rate is... I need some water, guys. 3.4%. So I was able to just... we already found what R was, so we can just say that for the last part. Now, this is a good point for me to stop this video. I will come back and record page 3 and page 4. And maybe I'll be able to do the same, go over section 2.5 in the same video. I wonder how long this one is, but I will have that one posted very soon. And also